Alrighty, section 4.0, and here is some geometry of a 2 by 2 determinant. And so if I have a triangle made up of the set 0, 0 for one coordinate, x1, y1 for another corner, and x2, y2 for a third corner, then it turns out that the area of my triangle, they're calling this triangle OPQ, so this is triangle O for origin, PQ. Then the area of OPQ is given by 1/2 the determinant of x1, y1, x2, y2. That's kind of cool. Okay, so we're saying that we'll put them out here in the positive quadrant like that. So here's some x1, y1 and some x2, y2, and at the origin, and it turns out if we take half the value of the determinant of that particular 2 by 2 matrix, we get that determinant. Now, so they go through the derivation of this thing, and they use actually polar coordinates to get this idea. And so if we take a look at this, then they're saying, okay, there's an angle theta 1, here's an angle alpha, and they're calling this one Q, that one P. And so let's just I'm going to go through kind of what they're going with here. And so they use polar coordinates, and so if this is oh, okay, so I need to change my x1 and x2s this way, okay, to match up with theirs. So x1 goes with P. But if I use polar coordinates, then and I call this R1 and I call this thing R2, then I know that x1 is equal to R1 sine theta 1, and sine, I was looking at their thing and not looking at what I was doing. Okay, cosine, so it's x1 is R1 cosine theta 1, and y1 is R1 sine theta 1. And then similarly, they then say that what? Oh no, they don't do that yet. So sorry, I'm just kind of following along with what they have. So we've got our R1, and it says, oh well, then the area of this thing, I'll just call it area, is equal to, they say, 1/2 the length OP. Okay, so that's our R1. So we'll go with, well, we'll do it like they do, OP. And then times OQ sine alpha. Okay, now this is R1 and this is R2 here. And now one of the things is, oh, okay, now do you agree with that, right? You know, so they are using a nice geometry formula here with, you know, this sine formula for area, where they take the lengths of those two sides and the sine of that angle in there, alpha, multiply that by 1/2 and get the area. Ah, okay. Well, so that's something to look up. I mean, you know, are you convinced that's the area? Is that, you know, that's coming from, I believe, the law of sines, and in getting that area. Off the top of my head, I would have to work through this to believe that, yes, that's the area, but we'll go with it. And so then they're going to say that OQ, they're going to also name, I got to get that in there, the bigger angle here. Now it's going to get messy. Let me draw it over here again. Just the angles. So they're saying that's theta 1, but then that whole thing is theta 2, so that alpha is equal to theta 2 minus theta 1. Okay? So that's what they put in there. So this is equal to 1/2, and they go with OP again and OQ, but now they say sine of theta 2 minus theta 1. Okay, and then they use a trig identity for the difference, sine of the difference of angles. So they got OP, OQ. And so now this is all times the sine of theta 2 cosine theta 1, and minus cosine theta 2 sine theta 1. So they're using a trig identity there. So plenty of trig in all this. And then they multiply through and regroup. So they say, okay, this is 1/2. And why they keep going with the OP and OQ, I don't know, but we'll stick with it. So if I take the OQ and set it with that one, so I need all four of these terms, but I can write them, the OP, the OQ, sine theta 2, cosine theta 1, I can write them in any order I want. And so I'll write them as OQ sine theta 2, and OP then next, cosine theta 1, and similarly I'll put the OQ with the cosine theta 2 here, and the OP, I'm running out of room, sine theta 1 there. And now they all of a sudden jump to the x1s and y1s and so forth. So you see, you know, this was R1, this, R2, this is R1, this is R2 and R1, and so again, you know, they start off pointing this out. Well, you've got the same sort of thing with theta 2 and R2. And so they point out that, that, since that's R2 sine theta 2, that's just Y2. That is just X1. And we have minus, here is R2 with a cosine, so that's X2, and then Y1. And so, if you have those coordinates, this formula for the area is just true. Okay, that's true no matter what. However, if you look at that matrix and you take the determinant, now, right, here was the matrix, x1 in the top and x2 in the bottom, x1, y1, x2, y2. If I take that determinant, I get x1, y2 minus x2, y1. And so if you look up here, right, that's what we have there. And so the determinant of this is almost that formula. And so now if we just throw 1/2 out in front, then we get that area. Okay, so it may or may not be something special about determinants. So they point this geometry out. Now, of course, an interesting question is, well, what about, could I do it with 3 points and a volume of a pyramid, right? 3 points in 3 dimensions. Is that the volume of a pyramid? Okay, a 3-sided pyramid, but a pyramid nonetheless. I don't know. Okay, it's okay. But an interesting question is, does the if you go through all this derivation and so forth, does that hold? And I don't know. I think that's an interesting question. I don't think they mention it. No, they don't do that. They do mention for a general triangle that all you have to do is subtract one of the points from the others. So see, if I have a general triangle, and suppose this is x1, y1, and x2, y2, and x3, y3, then if I subtract x1, y1 from each of the other points, what that does is it creates that same triangle but translated. And so this would be the x2 minus x1, y2 minus y1, and this would be the x3 minus x1 and y3 minus y1. Okay, now that would say then that the area here and the area here, of course, have to be the same, but I know how to find the area here, and so that would say that area, in this case, for a general triangle, is the determinant of the x2 minus x1 and y2 minus y1 and then x3 minus x1, and y3 minus y1. Oops, forgot my 1/2 out in front. So it would be the 1/2 of that. Now, notice, though, that if I think of these as matrices, okay, what I've done is I said this is 1/2 the determinant of the matrix x2, y2, x3, y3 minus the matrix x1, x1, y1, y1. And I can see geometrically that, because now I understand a geometric interpretation of this determinant with the 1/2 out in front, I can see that this determinant is the same as that determinant, and so it, when you notice things like this, it starts making you kind of wonder about theorems and so forth. Because, see, this was a very special thing we did. We subtracted the same thing from the first column over here, and we subtracted the same thing from the second column over here. So these two columns were exactly the same in this second matrix, and it ended up being, we were able to get a determinant that was similar to another problem. Okay, so so the question is, what can we do with that? And this is what the rest of the chapter is about, is looking at theorems. When we see that we did stuff like this and we were able to get this triangle by doing a subtraction and all that, can we find some theorems about equivalent determinants and what's out there? Okay, and so that's the rest of it. But there is an interesting geometric interpretation of the determinant.